the first lecture is pretty much about the scale of the universe. So in order to appreciate how large, how big the universe is, we got to do a little background into a scientific tool, a mathematical tool called scientific notation. So a lot of you might have had this in math, but you might have forgotten what scientific notation is and what its purpose is. In astronomy, it is very important. So the usefulness of scientific notation is that it allows us to write large numbers in shorthand notation. For example, in astronomy, we're always dealing with large numbers, such as the mass of the Earth. If I didn't have such a thing as a scientific notation, I would have to write this cumbersome number down. 6 followed by all these zeros. 3, 6, 9, 12, 15, 18, 21, 24 zeros, okay? So the mathematical tool of scientific notation allows me to go back 24 spaces and then nice and short, write down the mass of the Earth, 6.0 times 10 to the 24th. Now the number that I'm giving you is actually a kind of a rounded number. When you look at data tables, they give you a little bit more decimal places. They'll say something like 5.98 times 10 to the 24th. If you want to go out more decimal places, you can always find websites and things that they're going to go out more decimal places. But if you round it, it pretty much rounds to 6. 6 times 10 to the 24th. Mass of moon, also a very large number, but not as many zeros as the mass of the Earth. 6 times 10 to the 22, okay? Mass of sun. Sun, you would expect, is heavier, right? So mass of sun should have more zeros, which it does, 10 to the 30. And the number in front is 2. So that's basically 2 followed by 30 zeros. Imagine having to write that down. If you didn't have such a thing as scientific notation, you would have to write down 30 zeros. Waste your time. Very cumbersome. Mass of the Milky Way galaxy. Of course, this is an approximation. We do computer simulations based on our observations and things like that. And then we do a bunch of calculations, and then it pops up this number, 2 times 10 to the 42 kilogram. Notice how many zeros that is. 42 followed by 42 zeros. Okay, here's another example of something that is large that scientific notation could be helpful for. It's known as the speed of light. Speed of light is the fastest speed that is imaginable. It's the fastest speed that anything can go at. We use the symbol c for the speed of light. And what is it equal to? Well, there's different ways of saying the speed of light. You can say 186,000 miles per second. What does that mean? If you travel at the speed of light, in 1 second, you cover a distance of 186,000 miles. Talk about impressive. Can any runner go that fast? No. Can any aircraft go that fast? No. You know, in order to escape out of the gravitational field of the Earth, how fast does an aircraft have to go? Roughly about maybe 25,000 miles per hour. So man-made aircrafts and things like that can go fast. Maybe they can go 30,000 miles per hour. 30,000 miles per hour. This is 186,000 miles a second. You see the difference? Not per hour, a second. Okay? That's like you close your eye, you open your eye, the light has already traveled 186,000 miles. Okay, going at that speed, does anyone know how long it takes the light to get to us from the sun? Where? 8 minutes. You see how far the sun is from us? Way, way far. Even though light travels very fast, it gets to us 8 minutes from the sun. Okay? What does that mean? That means we see the sun as it was 8 minutes ago. We don't see the sun as it is now. So what? We're actually seeing the sun in the past. You see? 8 minutes in the past. If the sun, of course, God forbid this happens, if the sun disappeared right now, this very instant, how long would it take for us to know about it? Yeah, you see? So there's two ways of understanding this. If something were to happen to the sun, it takes 8 minutes for us to realize it. And the other way to look at it is you're looking 8 minutes into the past history of the sun. You see? It's taking the sun 8 minutes to get here. Okay, what's the different way of expressing this? 300,000 kilometers per second. Why? 1 mile is equal to 1.6 kilometer. So if you multiply this by 1.6, you get this. Okay, 300,000. Now, let's express this differently. A kilometer is 1,000 meters. So another way to write this, since each kilometer is 1,000 meters, is to add 3 zeros. So the speed of light is 300 million meters per second. 300 million meters per second, you see? Now, let's change that to scientific notation. How would I change to scientific notation? 3 times 10 to the 8. So how do you do that? 1, 2, 3, 4, 5, 6, 7, 8. 3 times 10 to the 8. So usually in data tables, if you look at official tables, they'll give you this number, 3.0 times 10 to the 8. If you really want more decimal places, it's probably something like 2.9999777, so on, so on, so on, so on. If you round it up, it becomes 3, you know. So this is the way that usually you'll see it written. You could also write it this way. If you go to the mile, how would you change this to scientific notation? Go back 1, go back 2, go back 3, go back 4, go back 5. For scientific notation, you always got to keep going until you end up 1 to the right of the first digit. So that means 1.86 times 10 to the 5th miles per second. Okay? What's another way of saying the speed of light? Well, this one is the easiest way of saying it. 186,000 miles per second. Okay? So if someone just kind of stops you and says, what's the speed of light? The easiest way to say it is 186,000 miles per second. Every second it goes 186,000 miles. If you want to express this scientific notation, either this way or this way. Okay? So those are all big, huge numbers. It gives you example. Okay. What's another good usefulness of scientific notation? Well, it allows us to compare two large numbers to each other. Suppose I wanted to compare the mass of the Earth to the mass of the Moon. The two examples from the previous page. What I do is I divide them. The mass of the Earth to the mass of the Moon. So usually this is something that I want you to know in general. Whenever you want to compare two numbers to each other, it's better to divide them, not subtract them, right? Suppose, let's just use another practical example. Suppose I have $10 in my pocket. Another person has $2 in their pocket. If you subtract them, you can say I have $8 more than them, okay? I have $8 greater, $8. But the better way, mathematical way to compare two things is to divide them. I have $10, they have $2. I have 5 times the amount of money. 10 divided by 2 gives you what? 5. I have 5 times the amount of money in my pocket than they do. So the division is usually what we do. So when you want to find out mass of Earth, divide by mass of Moon, 6 times 10 to the 24th, 6 times 10 to the 22. Well, in this case, it's an easy division because 6 cancels 6. 10 to the 24th over 10 to the 22, you subtract their power. If you got 24 zeros on the top, you got 22 zeros on the bottom, that means you're going to have 2 zeros on the top. 100. 10 squared. So what does that mean? This means that the Earth is 100 times heavier than the moon. So again, if someone comes, approaches you, says, how much heavier is the Earth? 100 times heavier. What's another way to visualize this? If you put the Earth on one side and you're trying to balance a scale, how many moons should you put on the other side? Okay, I'm not going to draw all 100. You get the idea, right? You got to put 100 moons on the other side to equal the weight of the Earth. Okay, so you can say moon has 100 times as much mass, also 100 times as much gravity. Okay, the weight. Now, if I were to ask how much bigger is the Earth than the moon, is it 100 times bigger? Oh, that's a different question. The mass is 100 times more, but you cannot say the Earth is 100 times bigger. By bigger, what do we mean then? Yeah, size. So in other words, if this is the Earth, how many moons does it take if I were to lay them end to end? How many moons can fit across the diameter of the Earth? That's what we're asking. So what should I divide? Their what? Starts with D, diameter. I got to divide the diameter of the Earth by the diameter of the moon. Or what else can I divide? It starts with R, radius. Since diameter and radius are just different by 2, one is double the other. So what I do here, I divide the radius of the Earth by the radius of the moon. Radius of Earth is 6,378 kilometers. Radius of moon, 1,738 kilometers. And I get 3.67. So you would say the Earth is 3.67 times larger or bigger than the moon. So what does that mean? If you take this, you can fit one of them, you can fit another one, you can fit another one, and then 67% of another one, something like that, So 3 full moons fit across the moon, the Earth, and a little bit more than half of a moon. If you want to remember it kind of quickly, you can round it up to 4. Say the Earth is 4 times bigger than the moon, roughly, There's another related question. I want to see who can get this one. How many Earths, if I were to open up the Earth, imagine the Earth is like a box. How many moons can I take and fit into the volume of the Earth? Do you see what I'm trying to ask? How many of these can I take? Imagine this is a huge bowl, and this is a bowl. How many of those balls would fit inside of that bowl? That's a different question, right? Okay. How many moons does it take to go and fill up inside the Earth and occupy the full volume? Okay, here's what you do. Does anyone know? Okay, it's a little trickier. Take the 4 that we approximated. We said this is approximately 4, right? So the Earth is 4 times bigger than the moon. How many moons will fit inside the Earth? 4 cubed. 64, approximately. You can literally take 64 moons and stuff it in there. Why do you think I cubed 4? Where does it come from? Anyone remember the equation for the volume of a sphere? You haven't used it for a while, right? Volume of a sphere is 4/3 pi r cubed. So the volume of a sphere is proportional to its radius what? Cubed. Right? So if this guy is 4 times bigger than that, its volume is 64 times the volume of that. because the volume is equal to the radius cubed, proportional to the radius cubed. Okay? So if you have two things like a basketball and a tennis ball. If you know the diameter of the basketball, the diameter of the tennis ball, you divide them, you find out how many times bigger the basketball is. Now, if you want to open up the basketball, put in tennis balls in there, how many tennis balls can you fit? The ratio of their diameter cubed. Okay? So you can do this to anything that you know of. Okay, example 2. Mass of the Milky Way divided by mass of Sun. That one, when you do it, you get what? 10 to the 12th. So I'm giving an example again from the previous page. So 2 and 2 cancel, 10 to the 42, 10 to the 30, 10 to the 12. What does 10 to the 12 mean? A quick way of saying 10 to the 12 is trillion. That means the Milky Way galaxy, I'm going to draw a rough picture of the Milky Way. And the sun is like here. Okay? The Milky Way galaxy is how many times heavier than the sun? The Milky Way galaxy is 1 trillion times heavier than the sun. So the sun's mass, even though it's so huge, it's nothing compared to the galaxy's mass. 1 trillion times the mass of the sun. So what's one way you can think of it? There are 1 trillion sun-like stars in our galaxy. So how many stars are there? Well, if the whole thing is 1 trillion times heavier than the sun, that means there's 1 trillion stars, roughly. Now, it ends up being a little less than trillion. Why? Because all of that mass is not just star mass. Some of it is gases that haven't formed stars yet. They haven't turned into stars, right? So it's not all that mass that is in the form of stars. So it ends up being, our approximation is, there's probably about 300 to 400 billion stars in the Milky Way. Not all of it is, not all of the trillion is stars. The rest of it is gases that are going to turn into stars one day. Now think about that, in the enormity of that. 300 to 400 billion stars. Okay? Of course, the very next thing that comes in your mind is there intelligent life in them? You know, do they have planets going around them? Is there intelligent life? Is there Earth-like planet? You know, and those are all the questions that we wonder about. Do other stars have planets? That's one of the topics we're going to cover when we get into the planet section. These are called extrasolar planets. Okay? Oh yeah, we've discovered roughly like 500, 600 other planets going around other stars. But have we discovered an Earth-like planet? Yes and no. You know, we have some evidence that there might be some Earth-like, yeah. Do they have oxygen? You know what I mean. Now it starts getting hard. Do they have intelligent life? Well, you know, not yet. We don't know, you know. Somebody did a calculation and an approximation, and I'll talk about this later on in the course too. They roughly estimated that every big galaxy in the universe has probably one intelligent life form in it. So even though there are that many stars, it's so difficult to have intelligent life. You need the right star, you need the right planet, you need a planet that has maybe oxygen or something, not too hot, not too cold, you know what I mean? So even though there are that many stars, our galaxy probably doesn't have another intelligent life form. We're probably the only one in our galaxy. But are there other galaxies? Oh yeah, you bet you. Milky Way is only one of billions and trillions of galaxies, you know. So is there possible that one of the other ones has intelligent life? Yeah, okay. We're going to end with this topic right now. It'll just take about a couple minutes. This is special powers of 10 that is good for you guys to know. 10 to the third. A quick way of saying it, 1,000. What's the symbol for it? Kilo. Kilogram, kilohertz, kilometers. That's 1,000 meters, kilometers. Okay? Kilohertz, 1,000 hertz. 10 to the sixth. How do you say it? Million. What's the symbol for it? Big M standing for mega. Okay, where do we use mega? In everyday language, computer language, what do we say? Megabytes. The first computer I had, Macintosh, Apple, had 40 megabytes of memory. Okay? Now you guys can go and get a little flash drive that has gigabytes. Okay? Did I give away my age? I shouldn't have said that. Okay? So yeah, we're really past the mega age, you know. Billion is what? Giga. 10 to the 9th billion giga. So that's now we're in the gigabyte. But of course now you can buy external hard drives. They're in tera. 10 to the 12th is trillion. You see here how I used it? 10 to the 12th. I said the Milky Way is a trillion times heavier. Well, that's it. 10 to the 12th trillion tera. So are there terabytes of memory? Yeah, you can now do. Maybe eventually we'll have flash drives, terabytes of memory. And then quadrillion, we're talking peta. Eventually we'll have that. Okay? So that's how many 10 to the 15. Then there's 10 to the 18, 10 to the 21. Eventually we'll probably have flash drives that have crazy amounts of memory. You can store all the world's knowledge in there. Okay, so we laid the foundation today, and then on Wednesday we're going to start covering the astronomical unit system, the light year, and the parsec. Okay, have a good couple days. Download the stuff that I told you from my website.